Welcome to my third video, students. We will be continuing sampling theory. Now let us start with the tests of significance for large samples. Okay, and for the large samples we are going to discuss around 3 to 4 tests. Among those, the first one here is test of significance of proportions, this one. So let us see what is the test static. So first let us consider a large sample such that the size of the sample n is supposed to be greater than 30. Let me remind you, whenever we say large sample, n is always greater than 30. And let us assume n, capital N such samples. Okay, so that means there are totally n number of samples whose size is, each of those is greater than 30. Alright, so we consider a group of samples. How many are there in that group? Capital N, such that small n is the size of each of the sample. You should not get confused here. And let us also assume that P is the probability of success of each member of it in the sample here. In this group of n samples, capital N samples, each member has a probability of success represented by P and probability of failure represented by Q, such that P plus Q always add up to give you 1. P plus Q is equal to 1. Okay, that means it follows a binomial expansion. So one should remember the limiting point of normal distribution is always binomial distribution, which you might have studied in your third module, that is probability distributions. So whenever n is very large, P and Q are not very small. That means they are almost nearer to each other, the success and the failure, and n is very large, always the normal distribution limits at the binomial distribution. Okay, so that's why here we consider P plus Q equal to 1. So here P and Q N and P are the binomial variates. So the binomial distribution now he is regarded as the sampling distribution of number of successes in the sample. Also, let us assume that the standard deviation of the distribution is under root of NPQ and the mean of the distribution divided by given by mu is NP, because binomial we know the mean is NP and the standard deviation is under root of NPQ. Now let us consider the proportion of successes. So mean proportions of successes is given by P. What is P here? Yes guys, P is equal to the mean proportion of successes. Similarly, the standard deviation or the standard error proportion of successes is given by under root of PQ by N. Got it? Under root of PQ by N. Now consider the test static given by Z, that is the standard normal variate, whose formula is Z is equal to x minus mu divided by sigma, where x represents the observed number of successes, that is in the practical situation how many times success is being achieved, and mu represents the mean number of successes from the theoretical part. Okay, from the given data we consider the mean number of successes, we find it, that is mu, but x is the actual number of successes. Okay, and the difference between the actual and the theoretical successes is the numerator of the test variate Z. And coming to the denominator, sigma is under root of NPQ. Got it? And one should remember always that the Z value, the hypothesis, if it has to be accepted, Z should lie within the range of plus minus 2.58. If it is beyond 2.58 or less than minus 2.58, then what happens? The success, the Z value, if it is like this, then the suggested hypothesis will not be accepted. If it is only in this range, then it is accepted, else rejected. That is how it is. Understood? Next, we also have something called the probable limits given by, because problems will be asked based on probable limits as well. So probable limits is given by p plus minus 2.58 into sigma value, which is under root of pq divided by n. This is the formula for the probable limits in the case of proportions. Understood? Now let us see a couple of examples based on these test of significance of proportions. Okay, let us see how the problems for test of significance of proportions can be. Alright, let us consider a situation. The question says result extracts reveal that in a certain school over a period of 5 years 725 students had passed and 615 students had failed. Now we need to test the hypothesis that the success and failure are in equal proportion. So success and failure is equal. That is the suggested hypothesis. Okay, so let us see how are we going to test it. All right, now the total number of students is given by number of failures plus number of students passed, which is equal to 1340. Okay, now observed proportion of successes. So 725 students have passed. So the proportion is obtained by 725 divided by the total, that is 1340, which is given by 0.54. Okay, similarly, suppose that the success and failure are in equal proportion. Usually whenever you take an exam, you throw a die, you throw a coin, you play you roll a die. In all the cases we consider equal probabilities. Here also let us assume we have equal probability of clearing the exam or passing the exam, and equal probability to fail as well, both the cases. So let us assume here the probability of the failure and success in the given exam is equal. Therefore P is equal to 1 by 2. Hence Q is also equal to 1 by 2. Right? Now anyways, so what is the difference here between the successes? Observed successes, that is observed proportion of success, and theoretical proportion of success. We have 1 by 2 is nothing but 0.5 is the theoretical value, and 0.54 is the observed value. The difference between these two is given by 0.04, which is nothing but our numerator. Understood? So once we come to the test static, z is equal to x minus mu divided by sigma. Sigma, how do you find it? Sigma is given by under root of n pq divided by n. Otherwise, root pq by n. Okay, square root of pq by n. So we know p, which is 0.5. We know q, that is also 0.5. And n is the total number of students here, which is 1340. So substituting and simplifying, we are going to get sigma, which is nothing but the standard deviation of proportions of the successes, given by 0.014. Substituting the values of difference and the standard deviation in the test static z, we get z is equal to 2.86. But we just discussed in the theoretical part that z is supposed to be between negative 2.58 and positive 2.58. Look at this, guys. So nobody will give you these values in the question. You got to remember them by heart and remember them. Understood? So if for every test you got to remember these standard critical values, so then only you can easily do it. Understood? So obtained value is 2.86, which is greater than the required range, that is, it is beyond 2.58. Hence I told you the suggested hypothesis that the failures and successes are in equal proportions is rejected. Got it? So if it is within the range, we will accept it. But in this case, it is outside the range. Hence, we are supposed to reject the hypothesis. This is how we can apply the theory part to solve a practical situation. Okay, let us go ahead and see one more problem as well. So let us see another problem. The question says, in 324 throws of a 6-faced die, an odd number turned up 181 times. It is reasonable to think that, is it reasonable to think that the die is an unbiased one? They are asking that you just have to check for the statement that the die is, the given die, whatever is being used here for the situation, is an unbiased die. This is the hypothesis, that is the suggested statement. We need to test whether the statement is supposed to be accepted or it is supposed to be rejected. Okay, so let us see how are we gonna do here. So consider the probability of turning up of an odd number as a success, because when a die is thrown, what is the probability of turning up an odd number? We have, when a die is thrown, we have 6 alternatives that we can get, and each of them are equally having equal number of chances to be coming. Okay, so we have altogether 6 options that we can get. Among this, what are the odd numbers when a die is thrown? 1, 3 and 5. So among 6, we have 3 successes. What is the probability of success? Which is equal to 3 by 6, that is 1 by 2. That means whenever we throw a die, we get an odd number in such that the probability is 1 by 2, and we don't get an odd number. That means we get an even number. The probability of getting an even is also 1 by 2. So equally distributed. Okay, so anyways, we know that Q is equal to 1 minus P, hence that is also equal to 1 by 2. And now expected number of successes. See, the die, once when it is thrown, the probability of getting success is 1 by 2. But the same experiment is repeated how many times? 324 times it is repeated. Therefore, theoretically, what you are supposed to get this number of successes? The theoretical number of successes is equal to 324 into the probability of being successful in one attempt. That is 1 by 2. So 324 into 1 by 2 is going to give you 162. So this is the expected proportions. Expected success of proportions. Now let us see what is observed. The practically how many times we got succeeded. It says that an odd number turned up how many times here? 181 times. 181 times we got successful. So what is the difference between these two, which is going to be our numerator for the test static? The difference between these two is 19. Okay, now that you know N, P and Q, substitute the values in the denominator to find the sigma. So we have the difference divided by under root of NPQ, that is 19 divided by under root of 324 into 1 by 2 into 1 by 2, which is going to give you 2.11, and we know that Z value is supposed to be less than 2.58, and of course the given value, the obtained value here 2.11 is less than 2.58. Hence our hypothesis is accepted. That means we can conclude confidently that the given die is an unbiased die. Understood? So we got to see an example for rejecting a hypothesis and an example for accepting the hypothesis as well. Also, we will see one more example based on the probable limits. Let us see another example here for proportions. The question says the mean and standard deviation of the maximum loads supported by 60 cables are 11.09 ounce and 0.73 tons respectively. Okay, 11.09 tons is the mean and 0.73 tons is the standard deviation. That's what we should understand. And we need to find different levels of that is 99% and 95%, both the confidence limits for the mean of the maximum loads of all cables produced by the company. Okay, so this is the question, and let us see how are we going to solve it. From the data, x bar is given, that is 11.09, and the standard deviation sigma is 0.73. At 95% confidence limits for the mean of maximum loads, what is the formula? We have 95%, the value is 1.96 is the critical value, plus minus 1.96. Hence, we have the formula as x bar plus x plus minus 1.96 into sigma divided by root n. These are the confidence limits. Okay, so what we'll do here, we'll substitute x bar value, that is 11.09 plus minus 1.96 as it is, and again we have sigma value known to us, that is given in the question, 0.73 divided by root n. What is n here? Just check what is n. N is the number of cables given by 60. So substituting all the values and simplifying, we get the confidence limits under 95% significance level. That is 11.09 plus 0.18, which is going to give you 10.91, and 11.09 minus 0.18, which is going to give you 10.91, and 11.09 plus 0.18, which is going to give you 11.27. So these are the confidence limits that we have under 95%. Okay, so that it can bear the maximum load. Now at 99%, the critical value is 2.58. So here also we substitute the same values. So we get 11.09 plus minus 2.58 into 0.73 divided by root 60 is going to give you 11.09 plus minus 0.24. That gives us 10.05 tons to 11.33 tons at 99% confidence limits for the maximum loads. Understood? So this is how we can find the limits. Also, we can check whether the hypothesis can be rejected or accepted depending on this given situation. We try to apply the test static also to check, and this is only to give the limits. Questions can be asked in any method, and you guys got to be very, very cautious even with the theoretical part. Okay, so this is all about the test of significance of proportions. In my next video, let us see the another text.